Welcome. We're going to look at verifying identities, and there's some basic ground rules first. You will work on one side only of an equation unless you're told to work on both sides. And the other thing, especially important, is that you do not cross over between sides. That's because we have not yet proven that the two sides are actually equal. Let's take a look at this first example so you can see how this works. So that equal sign really should have a question mark above it because we don't know for certain yet that the two sides are equal. Only if we show that separately the two sides can be equal by boiling this part down to the same as that's the left side, making that the same as the right side, that will prove that the two really are equal. But we're going to have to do things to the left side to make it equal to the right side. That is where many of the various identities and formulas in trigonometry will come into play. So here is the formulas list, and we're going to be using some of these, but especially we're going to be using the Pythagorean identities and some of the basic trig ones, such as what we call the reciprocal identities, the fact for cosecant, secant, and cotangent, that they're the reciprocals of the three main ones. Same things opposite otherwise, but those are the main things. And that tangent and cotangent involve cosine and sine. Those are the most important ones. We'll use the others at times as well. So let's come down here now and let's look at this one. The first rule of thumb when doing these is to try to change all of this, everything to sines and cosines. So we are only going to work on one side. We're going to take the numerator here is sine, but the cotangent is actually cosine of theta divided by sine of theta. And subtracting secant is 1 over cosine theta. So I am using two of the things, like this one here and this one here. This is a cotangent identity. And the other one is a reciprocal identity. Now that we've done that, we have to think about what else we can do. And one of the easiest things to work with is this one because we have a fraction. Well, not everyone says that they're easy, but they're actually possible. Think of that sine of theta as sine of theta over 1, and we are dividing cosine theta over sine theta. So this is a dividing symbol. But when you're dividing fractions, what you're actually doing is that you're multiplying the reciprocal. Okay, cosine theta. So what we get as a result of this is we get, and I'm going to bring this over to here, we're going to get sine times sine, so I have sine squared theta over cosine theta minus 1 over cosine theta. We have the same denominators now. Let's see if I can get this. Okay. I don't want them all to disappear on me. Let's get it. This and this, because they're the same denominator, that means we can add the tops of the fractions. So we get sine squared minus 1 over these two combined, just cosine theta. That's the same concept as if it was 3 over 7 plus 1 over 7 would be equal to 4 over 7. It's just that concept from fractions. And we can do it with trigonometric functions, just like I showed here with the cosine. Well, now, let's see. We have used up this, and we've used up this here. We put them together to get over to this thing. And now we look at sine squared minus 1. And when you look at the Pythagorean identities, you see that that's equal. Well, actually, let's work out how that's equal to the cosine to negative cosine squared theta. Okay, I'm going to come over to here and write down a Pythagorean identity that has sine and cosine in it. Okay. So if I want to get this, I'm sorry, I want for this to all be together, and it doesn't quite stay. Okay, this I want from this. Well, that means that the 1 has to go to the other side, and the cosine squared theta has to go to the other side to get out of the way. So what I'm going to do is subtract 1 from both sides, but I'm also going to subtract cosine squared theta from both sides. So this and this make a 0, this and this make a 0, and we end up with sine squared theta minus 1 is equal to negative cosine squared theta. So I can just literally replace sine squared, whoops, supposed to be a theta there, minus 1 is equal to negative cosine squared theta, and that's because of the Pythagorean identity. Pythagorean identity. So what's really important here is that you can manipulate these identities as long as you apply normal rules of algebra to do so. On the bottom, we have a cosine theta. So think about what the squared means. Well, if we have a negative, that's like having a negative 1 there. And we have a cosine theta times another cosine theta. That's what squared means. On the bottom, we have a cosine theta. So it means that we can cancel out these, and we get negative cosine theta. And that is what we were trying to get to in the first place. So these two are equal. And because they're equal, it means check. This is verified as a true identity. So let's take a look at another one that does something different. We're going to verify this identity. Usually, I would immediately take everything and put it into sine and cosine. But I see what looks like a Pythagorean identity, and it actually is. Tangent squared theta plus 1 is equal to the secant of theta. So I am going to do the secant squared of theta. I should have said squared before, right? Secant squared theta. And now I'm going to work with the bottom part. So I have sine theta. The tangent is sine theta over cosine theta. And the secant here is 1 over cosine theta, and that's a plus 1. So let's continue to work here. Oh, let's see, it says work on both sides. So I'm going to come back to the other side in a moment. But let's keep going here. What I now see is I have secant squared theta, and here I have a sine squared theta. Underneath it, a cosine squared theta. That's these two and these two, plus 1. Well, plus 1, a 1 is weird. It doesn't fit. It doesn't have trig stuff with it, but it's actually extremely useful because I can make 1 equal to anything, 7 over 7. I can make it equal to negative 15 over negative 15 if I feel like. I can also make 1 equal to cosine squared theta over cosine squared theta so that I have the same denominator on the bottom. So let's now rewrite this. There's the numerator. I have sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta. So let's put these together. Secant squared theta. Well, I can put because I have fractions, I can do the tops of them being added. And these denominators are the same. Oh, now look at this. That is a Pythagorean identity. So that's secant squared theta over 1 over cosine squared theta. So now that I have that, let's think about what I would do. In fact, actually now that secant squared theta, well, I just realized secant squared theta is 1 over cosine squared theta. That's what that is. And I have this on the bottom too, 1 over cosine squared theta. Oh, this over itself is equal to 1. You can't get any simpler than that right now. We've got 1 here. So we need to see if the other side will get 1. Let's look at what steps I did here first. So the first thing I did was I used a Pythagorean identity. The second thing I did is I changed to sine and cosine for the tangent and the secant. And the third thing I did was the multiplying to get the squares. The fourth thing I did was using the number 1 here. Fifth thing I did was that then I added the fractions together. And that allowed me for my sixth thing to put a 1 there. And the seventh thing was to change secant of squared theta into 1 over cosine squared theta. And the eighth step, I got the number 1. Wow, a lot of steps to it, but each one of those steps are things you can do with trigonometric identities, and that's what most of them are here, or fraction work in a number of cases. Now let's take a look at this one up here, secant squared theta minus tangent squared theta. There are at least a couple of ways to do it. I could do it like this, where I start doing sine and cosine for everything, but it seems pretty familiar as a Pythagorean identity. So let's take a look at the Pythagorean identity that fits these things. I look at, I'm going to go over here to the side for this. Tangent squared of theta plus 1 is equal to secant squared of theta. Well, imagine if I just simply subtracted tangent squared theta minus tangent squared theta. I would have that 1 equals secant squared theta minus tangent squared theta. And this is what we have here. So if this is equal to 1, then this is equal to 1. And I got 1, and I got 1. I got 1 down here by manipulating the left side, and I got 1 up here on the right side. Yes, I manipulated it, but I didn't have to manipulate it much. I just used the Pythagorean identity in one thing, and I have that this is equal to 1. But because these two things match each other, I have proven that the identity is true. Right. Since I worked on either one or both sides, I was able to verify this identity. Check, verified. This one's different from the last one because of using Pythagorean identities instead of just simply using changing everything to sine and cosine. Yes, I used the Pythagorean identity in the first one, but I started off with changing everything to sine and cosine. Here, starting off with sine and cosine for this part was actually not the best thing. Over here, I could have done that, and I could show working it out, but I think this one's a pretty good way of doing it. Using a Pythagorean identity immediately gets us to where we want to be. Right. Let's take a look at this one, this problem, which is going to show something slightly different. Okay. Look at my steps on these. All right. So here I don't see, for 3 of the 4 things, there's nothing unusual. This one, though, looks like a Pythagorean identity. And it is indeed. Sine squared theta plus cosine squared theta equals 1. So let's do subtracting cosine squared theta. And so we get 1 minus cosine squared theta with all of this gone. And that means that this is sine squared theta. Now we have to work on both sides. So to give enough room, I'm going to go like this down most of the page. So I just started the left side, so let's continue. And for tangent, I am going to write that as a tangent identity, which means instead of tangent, I'm going to use sine over cosine. This is also a reminder that you're using the same rules for the squares as you would if they weren't squared. And that's like allowed. And sine squared theta. Now, since this is on the bottom of the fraction, I can like make it its own fraction there. So what I have is sine squared theta over cosine squared theta divided by that. So let's write that out. Sine squared theta over cosine squared theta divided by sine squared theta over 1. Okay. So now that I have that, let's multiply by the reciprocal, sine squared theta over cosine squared theta times 1 over sine squared theta. And that allows us to cancel these out. So as a final, I have 1 over cosine squared theta. Doesn't look like it too much to do that. I could call that 1 over cosine squared theta. If I wanted to, I could call that secant squared theta. All right. Now, I don't know which one will best because back up here, we need to work on this side because it says work on both sides. So I'm going to change them to the sine and cosines, which means secant is 1 over cosine theta divided by cosine theta, and that's cosine theta like over 1. So what I'll do now is this is dividing, so that's 1 over cosine theta divided by cosine theta over 1. So now I'll do the reciprocal because that's what you do with fractions. Oh, so now it looks like I can do 1 over cosine squared theta, and right here I have them the same. I could go further and call this secant squared theta, but no reason really. These two sides are equal, and that means what we have is verified. We verified that the two sides are equal, that this is a correct identity. Oh, there. Okay. Erase that part. It's not going to stay. And that shows you how to work with the identities. You can't cross over the equal sign by adding or subtracting on both sides, like what is called the properties of equality. And you only work on both sides if you're told to. Otherwise, you work on one side. But the goal is to get the two sides the same, and that proves that the identity is verified. I hope this helps for understanding some of the things about this section. Okay, I'll come back up to that. And thank you for watching and listening.